If I'm an engineer and my cargo pump stops, I really need to know, did it trip on a normal overload or did a fuse blow from a short circuit?
Yes. If it tripped on short circuit, you shouldn't just try to reset the contactor from the screen. You need to physically check if the fuses are gone. If you try to reset it without replacing blown fuses, you are essentially closing a circuit with a gap in it, which single phases the motor, or you're closing right back onto a dead fault.
Let's move to something that sounds genuinely terrifying on a gas carrier. Sparks. Specifically, earthing and ground faults. The document goes deep into the earthing philosophy.
This is critical. The 6.6 kV system on hull 1810 uses what we call an isolated ground, or an IT system.
What is the baseline rule for an isolated system?
Think about your house. The neutral wire is connected to the literal earth. If you touch a live wire, you get shocked because the current flows through you to the ground to complete the circuit. On this ship, the entire electrical system is isolated from the steel hull. It floats.
So if I touch a live 6.6 kV wire and the steel hull of the ship at the same time, nothing happens.
Theoretically, no massive current flows because there is no loop back to the source. In reality, there is a tiny bit of capacitive current, but not enough to cause a massive arc flash immediately.
Why design it that way? Why not ground it?
Reliability. Imagine you are in the middle of the ocean, propelling the ship through a storm. A minor insulation leak happens on a propulsion motor, causing a ground fault. In a grounded system, boom, the breaker trips instantly. You lose propulsion. You are drifting dead in the water.
But on an isolated system...
On an isolated system, the earth fault alarm goes off in the control room, but the ship keeps running. You have time to safely find the fault and fix it on your own terms.
Okay, but we are carrying liquefied natural gas. If there is a fault inside the gas tank, you don't want to fix it on your own terms later.
Exactly. And that is the massive exception in the earthing philosophy. The hazardous areas, specifically the cargo pumps.
Right, because those cargo pumps sit at the bottom of tanks full of LNG vapor.
Exactly. If you have an earth fault there, even a small spark could be catastrophic. So the rule completely changes. The source document is very specific. If an earth fault is detected on a feeder going to a hazardous area, the system does not just alarm.
It trips.
It trips and it blocks.
And then
Immediate.
Walk us through the operator protocol there. The alarm sounds in the control room, earth fault. What are the step-by-step actions?
Step 1, you look at the protection unit display. If it is a general feeder, you just get the alarm. You start searching, but the ship runs. But if it is a cargo pump, the RM unit will show tripped and blocked.
And I can't just press the reset button on the screen.
Absolutely not. The block means the lockout relay, specifically the K86 relay, is active. You cannot close that breaker again until you physically go down to the switchboard room, find the fault, fix the actual issue, and then manually reset that physical K86 lockout relay. The system forces you to acknowledge the danger.
It forces a human to take responsibility. You can't just keep hitting reset hoping a ghost in the machine goes away.
Precisely. You can't gamble with a gas tank.
That is reassuring, actually. Now, let's talk about another nightmare scenario. The blackout, or rather, the system's desperate attempt to avoid one. The document details a load shedding system. This is when the ship is demanding more power than the generators can physically give.
Right. The system has to decide what to turn off to save the rest of the grid. It's cutting weight to keep the ship afloat, electrically speaking. It does this in 3 distinct stages, or steps.
Okay, what is step 1, the warning shot?
Step 1 happens if a generator is loaded to more than 105% of its capacity for 20 seconds. The system basically says, all right, we're redlining here. It sends a signal to the low voltage, the 450V boards, to trip non-essential small items.
Things like the galley stoves or the air conditioning.
Exactly. Stuff the crew can live without for a few minutes. It's the ship saying, I'm busy, stop cooking dinner.
But what if that is not enough? The load just keeps climbing.
Then we hit step 2. This is the axe. This happens if the generator hits its instantaneous overcurrent limit. Basically, the breaker is milliseconds away from tripping to save itself from melting.
The system has to dump massive weight right now. What goes? The document has a specific list for step 2.
It does, and it's vital to remember. Step 2 disconnects 3 major things. 1, all cargo pumps. 2, both high-duty compressors. And 3, the bow thruster.
Wow. It just kills the entire cargo operation instantly. And the thruster.
Instantly. If you are maneuvering in port and step 2 hits, you lose your thruster and your cargo operation just like that. But it is better to lose the pumps than to lose the generators and go completely dark. If the generators trip, you lose propulsion and pumps and steering. This way, you stay moving, even if you stop pumping.
And you mentioned something called a forced trip in the notes.
Yes, this is an interesting piece of logic. If a generator actually trips, meaning it goes offline unexpectedly because of a mechanical engine failure, the system essentially panics. It assumes the remaining generators cannot handle the sudden massive transfer of load. So it immediately triggers the step 2 disconnects, dumping all pumps and thrusters to prevent the shock of that load falling onto the remaining generators.
It is ruthless efficiency. It anticipates a cascading blackout and stops it before it even starts.
Exactly. It sacrifices the cargo mission to save the ship.
Speaking of the bow thruster, that is a really unique piece of equipment in this document. It is huge, 2,000 kilowatts.
It is massive. And because it's so big, it uses a massive auto transformer to step the voltage down for the motor start. But maintaining this thing and the other main transformers introduces us to the mechanical safety of the switchboard. The keys.
I love this part. It reads like a puzzle box or a bank vault. Tell us about the interlocks on the transformers. How do we safely energize or maintain them?
Okay, so high voltage transformers are incredibly dangerous. You never want to open the door to the transformer room while it is energized. The Samsung 1810 system uses a trapped key sequence, specifically a Castell key system.
How does that work step by step? Let's say I need to open the transformer door for maintenance.
You go to the breaker panel. First, you have to rack the breaker out to the test position. This physically disconnects the power from the bus bars, but you still cannot get the key to the door.
Okay, so the main power is cut. Why can't I get the key?
Because there might be residual charge left in the massive windings. Next, you have to physically close the earth switch. This connects the bus bars to ground, draining any residual charge.
Safety grounding.
Correct. Only when the earth switch is mechanically locked in the closed position does a physical key release from the panel.
And that key?
That key is the only thing that opens the door to the actual transformer room.
So it is physically impossible to stand in front of the transformer windings unless the power is cut and the ground is securely connected.
Exactly. You cannot cheat the system because the key literally isn't in your hand until the safety steps are completed in order. And when you want to energize it again, the sequence reverses. You have to lock the door, put the key back in the panel, open the earth switch, and only then will the system give you the CB-ready light to close the breaker.
That is brilliant analog engineering. We have covered flow, control voltages, protection, and safety. I want to wrap up by synthesizing all this from the perspective of the person actually running this. If you are an experienced chief engineer on Hull 1810, how does this knowledge change how you operate compared to a rookie?
Well, we've talked about the what, but the how really depends on experience. If I'm an experienced chief on this ship, there are 3 very specific emergency scenarios that I handle very differently from a new engineer.
Give us scenario A.
Scenario A is load shedding anticipation. A rookie waits for the alarm. They let the automated system handle it. A veteran watches that 105% timer, the step 1 warning, like an absolute hawk.
Why not just let step 2 handle it?
Because if you hit step 2, you lose all your cargo pumps instantly. Imagine you're in the middle of offloading LNG at a terminal. You are pumping 10,000 cubic meters an hour. A sudden shutdown creates massive pressure waves, water hammer in the pipes. It damages equipment, it delays the schedule, and it really annoys the port authorities.
So the veteran reduces the pumping rate manually before the system fires the axe?
Correct. They manage the load to stay just under the limit. They save the operation by being proactive instead of reactive.
That makes total sense. What is scenario B?
Scenario B is the ghost fault. You get an earth fault alarm. A rookie might panic, or worse, ignore it because the ship is still running.
But the veteran looks at the exact location. Main board versus cargo board.
Exactly. If it is a general alarm on the main board, the veteran knows, okay, we have a leak, but the ship is safely running. I'll start isolating non-essential circuits one by one to find it. But if they see it as a hazardous area trip, a cargo pump, they know, do not touch that reset button.
Because that's a fireable offense.
It's a potentially deadly offense. Trying to force reset a blocked cargo pump breaker could cause a spark in a gas zone. The veteran knows the critical difference between a nuisance alarm and a stop work authority situation. They respect the gas.
And scenario C?
Scenario C involves the vacuum contactors we discussed. Let's say a cargo pump trips. The display says short circuit. A rookie might just verify the pump motor looks okay from the outside and try to reset the breaker from the screen.
But the veteran remembers the fuses.
Right. The veteran knows the vacuum contactor cannot break a short circuit. If the protection relay says short circuit, the veteran immediately grabs a multimeter, goes to the board, and checks those fuses.
Because if the fuses are blown and you try to reset...
If you try to close a contactor with blown fuses, you are causing single phasing, which burns out the motor, or you are closing onto a dead fault, which could literally explode the contactor. They know the physical limitations of the hardware, not just what the screen says.
It really comes down to knowing not just which button to push, but what mechanically happens inside the box when you push it.
That is the difference between just operating a ship and truly understanding it. On the 6.6 kVv board, the difference between a minor alarm and a total blackout is knowing exactly which breaker feeds which pump and why the lights just flickered.
Which brings up a really provocative thought to leave you with. In an era where ships are becoming increasingly digital, where everything is controlled by touchscreens and software, the ultimate safety of this massive LNG carrier still relies on trapped physical Castell keys and heavy mechanical springs. The digital brain is useless without the analog muscle. It makes you wonder how far we can actually push automation before we lose that physical guarantee of safety.
It's a great point. Sometimes the oldest technology is still the safest.
Absolutely. Well, that is a perfect place to dock this deep dive. We've gone from the diesel generators to the fuse box of the cargo pumps.
It is an impressive system,
Yeah.
complex but entirely logical when you break it down.
It really is. To you listening, next time you see a massive ship on the horizon, just remember the silent, high-voltage ballet happening inside those steel cabinets. Thanks for joining us on this deep dive.
Safe sailing out there.